Okay, good morning, everyone. This is a seminar that is part of the Distinguished Speaker Talk series hosted by the Global Computing Lab. It's a research lab in high-performance computing, data analytics, and interdisciplinary sciences at the University of Tennessee, Knoxville. I am Michaela Tauper. I'm the lead of the group. And we are hosting this seminar on a monthly basis. This is the third this semester. And stay tuned for the next one. But today we are thrilled to welcome Dr. Amy Roberts. Amy is a professor, assistant professor at the University of Colorado, Denver. And she's in the Department of Physics and is specialized in building tools that improve access to scientific data analytics. And her talk today is about innovative method for building trust in a result that discover dark matter. So fascinating topic. We are thrilled to have Amy here. She is remote, and in her room she has also a couple of hosts. We also want to welcome our online host and new participant in this seminar from Oak Ridge and University of Tennessee, Knoxville in Astrophysics Department. Amy, you have 30 minutes, and we are very excited about your talk. Welcome.
Thank you so much. I'm so glad to be here virtually. So the first thing that I want to mention is I'm going to be talking about trusting dark matter results, and there's a link here, and it's not accurate. So I'll actually provide the accurate link, and it'll be in the description of the video once it's up. So I'm going to be talking about dark matter and why it's so difficult to detect dark matter and what we can do to increase trust in our dark matter results. So let's go ahead and get started. Here we go. Okay, so I wanted to very briefly introduce. Is it showing up?
Yes.
Yeah. Great. Okay, so this isn't me. This is Chris Morris. He's a wonderful physicist that I got to work with when I was at Los Alamos National Lab. So I wanted to give you just a little bit of background about me. So I'm an experimental nuclear physicist. So yeah, nuclear structure. Big fan. And my background is actually really in the nuts and bolts of detector building and detector characterization. So that's really, so we have here a couple pictures. These are detectors that I actually contributed to building right here. And now I've sort of gotten, over my career, I've gotten progressively more ambitious, and am now trying to detect particles that we don't even know exist. And so that's where I am right now with CDMS. So my perspective is really coming from like a physical hardware nuts and bolts, literal nuts and bolts, what bolts do we use kind of perspective. And so this is really sort of the very heavily experimental track was the track that I was on for a long time, all through graduate school, all through undergraduate, and then for most of my postdoc career as well. But you know, as a female presenting person in an experimental physics lab, I got really sick of people trying to tell me how to use a wrench. And so what I did was I sort of switched over to the computing side, and that has been just this really wonderful refuge. And it's actually been really nice because we need people in computing who have a strong experimental background and really understand the details of the experiment. So we're going to get into that a little bit later. What a lot of the details of the actual physical experiment mean are really for the data collection. They're metadata that's really important to the interpretation of the data. So we'll talk about that a little bit later, but I just kind of wanted to give you a sense of my background. So I'm really a detector person, and the thing that really drew me to CDMS was these amazing detectors that they make. And if any of you are familiar with dark matter experiments, you know that these detection mechanisms that these use are just truly amazing because they're looking for such small signals. So they're incredibly sensitive detectors. Okay, so that's a little bit about my background. Let's talk about dark matter. So what I'm going to do is I'm going to show you a video, but first I want to ask everyone a question. So I'm so sorry for the people online. This is a little bit difficult. So for the people online, I'm going to have you look at the objects around you. And for the people who are in person, I want you to look around at the people who are next to you. And if you imagine that you're all planets, just think for a moment, what does gravity say you're going to do if you're all planets? Okay, I'm going to pause and let you think about this. You can check in with each other. What's going to happen?
We're going to move closer to each other.
We probably.
Yes.
Attractive
Yes,
channel?
okay. We're all physicists. So for the people, for my people online, I apologize. You don't have any other people planets, but if you just look at the objects around you, your computer, if you and your computer were out in space, you would slowly drift towards each other. Okay, so that's what's going to happen. So let's take a look. Going to take it a moment. Sorry, I promise it's worth it though. So what we're going to do is we're going to, oh no. That's okay. Okay, it's a little bit smaller. All right, so what we're going to do is we're going to look at something. All right, I just have to be very precise.
You cannot move the mouse.
I can't move them out. All right, so I'm just gonna have to go into it. So what we're gonna start seeing here is it doing anything? No, it's not doing anything.
Let's try again.
There we go. What we're going to see here is we're looking at the early universe. And this blue stuff is actually hypothesized dark matter. So this is from a simulation of the early universe. So what we're seeing here is that the main thing about dark matter is that it has mass. And so all of that mass is clumping together. And as all of that mass clumps together, you start seeing pink. Do you guys see the pink there?
Mm-hmm.
The pink is hydrogen. So because there are these clumps of mass from the dark matter, the hydrogen starts also clumping. And now the hydrogen is clumping enough that it's able to start forming stars. So we're going to watch for a little bit. You see more and more pink is accumulating. And there we have a little explosion. So now we're starting to see these stars burn and produce heavier elements. That's what the green is the heavier elements above hydrogen. So heavy elements like carbon. There we go. Okay, and all of that. So I'm going to pause this. I'm going to try to pause it. Okay, I succeeded. So all of this happened because of that early clumping from the dark matter. So the dark matter again had that mass, and so it pulled itself into these sort of clumpy strands, and then that started pulling in ordinary matter, the matter that we're familiar with, like the sun. Well, so it started with hydrogen, and then as the hydrogen started coming in more and more, again, there are more and more masses developing, and then you can start building stars. So what I want to mention, this is just one piece of our evidence for dark matter. I'm not going to go through all of them, but it's a really strong piece. It's what the universe looks like as we look back in time. And what you can see here is there's this Sloan Digital Sky Survey. We've got a little bit of data over here on the rightmost corner that was taken with this beautiful telescope. And what that's showing you is sort of the clumpiness of our universe, the clumpiness of matter in our universe. Each one of those dots is a star. So what we're seeing is that the universe has this, it's not uniformly, stars aren't uniformly distributed through our universe. They're sort of in these clumped strands. And we can only get that in simulations if we first assume that we have some kind of mass that doesn't interact with other matter, but that does have mass, and so it interacts gravitationally and starts that clumping process. And there's got to be a lot of it. So this is kind of our basic, so where a lot of our constraints on dark matter come from. There are other places that give us other constraints on dark matter, but this really kind of says, you know, we want something that's relatively cool. If it's moving too fast, then it won't be able to clump very well. And we have some idea of the mass density. So we know, you know, like how much the universe is and how much mass we need to put in our early simulations of the universe to cause the amount of clumping that we see in our data. So that gives us some information about this thing that we're calling dark matter. But it doesn't give us a whole lot. Like, so now if you're an experimentalist and you want to go find dark matter, what you face is this problem. So we have some constraints on the mass density, but that's different than having a constraint on the mass of an individual particle, because we could have, you know, really heavy particles and relatively few of them, or we could have a lot of extremely light particles, and that would give us the same astrophysical results. So what I want to highlight here is that when you're designing for dark matter, you're looking for something that's incredibly light, like 10 to the minus 22 eV. So that's, let's give a scale here. A GeV is about the mass of a proton. So that's not terribly heavy. And then over here, we've got 10 solar masses. So we have dark matter candidates that range all the way to much, much smaller than the mass of a proton, which is already pretty small, all the way through the mass of a proton up to 10 solar masses. So if you're trying to detect this, the problem that you have to face is how do you build a detector when you don't even know what the mass is? The detector that you build for something that's many times smaller than the mass of a proton is very different than the detector you build for something that's 10 solar masses heavy. Okay, so this is the problem that all dark matter experiments face. And the CDMS detector, the detector that the experiment that I participate in, we are sort of focused on this mass of a proton region. But there's increasing interest in this entire range because we haven't found anything. We really thought that we would find something. And now that we haven't found anything, we're starting to more seriously consider, well, what if it's much lighter than a proton? What if it's much heavier than a proton? And so one of the things that we're seeing in the field today is this explosion of small dark matter experiments that are testing new detector technology to look for very different masses. Okay, so I wanted to give you an idea of the landscape. So let's talk about what's happening here. So the idea that we have, the mental idea that we have when we think about dark matter is that dark matter is everywhere. So we saw in that simulation, the blue areas. And so the Milky Way is in one of those blue areas, is what we think. And we have evidence for that. So what we think is happening is that there's just this dark matter background that we're all sort of swimming in and we don't even notice it. If you're familiar with neutrinos at all, this is very similar to neutrinos. So we have neutrinos coming from the sun. They interact with matter, but only very rarely. So right now, you have neutrinos just streaming through you from radioactive processes in the sun. It's very cool, and it can be very alarming to find that out suddenly. So I'm sorry, it's early in the morning for that kind of news. So we have all of these. So our mental model is that like neutrinos, we have all of these dark matter particles that are just streaming through our world and only very rarely interacting with us. And so that's what I'm trying to show in this picture here. So here we have an old style CDMS detector. This experiment that this detector was from was recently decommissioned, and we're currently building the new one. But it's very similar to our new version. So it's a crystal, so it's ordinary matter. And what we're hoping is that dark matter doesn't interact with matter very often. We know that. But we're hoping that every great once in a while, it will interact with ordinary matter. And so what we're imagining is that there's this everywhere on the planet, there's this stream of dark matter particles, and every once in a while, one of them might hit and interact with the nucleus in our detector, and then give us some kind of signal. So you can kind of see very lightly on here, there are these nice little pads that are etched out, and these are the sensors that we have on the detectors, and we're going to talk more about those in a second. Okay, so this is kind of our model. We have this like wind that's just moving through us constantly. And what we need, and what physicists are hoping, what dark matter direct detection experimentalists are hoping, is that dark matter interacts frequently enough that we might actually be able to see one of these if we wait for long enough with the right detectors. We're very hopeful. We're very hopeful people. Okay. So this again is just kind of another, mental model. What do you picture when you think of this? So what you can picture is that you have this dark matter particle that's labeled a WIMP. So that's about the mass of somewhere between a proton and a germanium nucleus. And it comes in and it hits this nucleus. So that's this billiard ball. So let me show you with my mouse. So over here, we have our dark matter particle, and it comes in and it hits this nucleus. Now, pool balls is actually an astonishingly good analogy for dark matter. So we really do think, typically in the field, we think about dark matter as having what we call an elastic collision with the nucleus. There are some exceptions to that, and we're considering, like I said, because we haven't found anything, we're considering a bunch of different models. So there are some variations on this, but this is what most of us start with. And so the idea here is that when you build your detector, you want to choose your nucleus so that it's well matched to the mass of dark matter that you think is out there. So this is kind of a guessing game, right? So you say, okay, I think that the dark matter mass is maybe that of a silicon atom. And so then you go and you build our silicon nucleus. And so then you go and you build silicon detectors. And because when the masses are matched, then you're going to have maximum energy transfer. So if you've ever played pool, you know that when you hit the balls, if you hit it dead on, you can completely transfer the energy from your cue ball to your the ball that you're striking if they're the same mass. If they're not the same mass, then you're not going to be able to transfer as much energy. So we want to get as much signal as possible. And so that's why this detector design is so tricky, because we don't know what the mass is. So we don't know how to optimize our detectors for the mass of the dark matter. And so most experiments are essentially guessing at a mass and then deciding that we're going to be sensitive to a particular mass range. And if you want to be sensitive to a different mass range, you typically have to go make a whole different detector. And that's one of the things that we're seeing in the field right now. Okay, so now we're going to go on and we're going to look at the signals. So I just want to pause and say, I know it's 30 minutes, but does anyone have any urgent questions at this point?
We are all petrified thinking about all the dark matter around us.
Even it's busy. Okay. So the idea here is, so what I'm going to ask you to do here is I'm going to ask you to imagine that you are a sensor. You are a sensor, right? You are sensitive to, like, we have a lot of sensors on our bodies, actually. One of the things that we're sensitive to is heat. So just imagine that you're sitting there on the floor, or you're attached to your chair, which is attached to the floor. And what you are able to detect is changes in temperature. And you're maybe not able to detect, you have some sensitivity. You're sensitive to changes in temperature, like, if it went up 10 degrees Fahrenheit, you would definitely notice that. These are exactly the same. They're temperature sensors, but they're temperature sensors that are sensitive to incredibly small temperature changes. And so I'll talk more about that if you guys are interested, but that's all I'm going to say right now is that the temperature changes that we're looking at are, the idea here is that when you have a particle that comes in and hits a nucleus, that makes the nuclear lattice rattle a little bit. And that is a little bit extra. And that is the temperature that we're sensing with our sensors. So that's an incredibly small amount of energy. Okay, so now we're going to talk a little bit about how we do our data analysis. So this is what our sensors, this is a very simplified version of our detectors, and I apologize to everyone in advance of this because I'm going to ask you to sing and also hold hands. I promise it's relevant. So, okay, so what I want you to do is, you guys are down, you have a table in the room, right? So I'm going to ask you to imagine a split down the table. So you're sensitive to, and the floor is your detector. So you're sensitive to two different areas on the floor. So I'm going to ask everyone on one side of the table to hold hands if you're comfortable with that, and everyone on the other side of the table to hold hands. The reason is, even though you're individual sensors, we can't afford the wires to read you all out individually. So we have to link you all together and read you out as one single sensor. So, okay, perfect. Okay, and now what we're going to do is we're going to say, so one side of the table is responsible for the left side of the screen, and one side of the table is responsible for the right side of the screen. Do you guys, which side is which? Do you know which side you're on?
And we are the right.
Okay, perfect. Okay, so we're just going to sing this, and then we're going to sort of say what we think is happening here physically. So remember, you're attached to the floor, and you feel it heating up a little bit, and then you cool it back down. And it's going to heat up a little bit because there's some kind of interaction happening in the floor. Something went slightly radioactive and warmed things up. And then we have the air conditioning that's going to bring the room back down to the base temperature. Okay, all right, so I'm gonna count. I'm gonna be on this side with the larger pulse. So I'll go 3, 2, 1, and then we'll sing on 1. Okay, thank you all. I'm sorry. Okay, 3, 2, 1. Ah. You guys got it?
I have to do it?
Everyone has to do it. You're the sensors.
Okay, the part on the right?
Yes.
Okay.
Okay.
Yeah. Okay,
Yeah.
all right, I'll count down again. All right, do you guys see where, so I'm asking, so you guys know which sensor you are, right?
Yeah.
Okay, all right, so I'll count on 3, and I'll count down, and then we'll sing on 1. All right,
Okay.
3, 2, 1. You guys can't just make Michaela sing. All right, well, okay, we're gonna do one more. But first, let's talk about what's happening in this event. Okay, so everyone felt the floor warm up, and that makes sense because the floor is connected, right? So if one side of the room warms up, the other side of the room is going to warm up a little bit as well. But one side of the room warmed up more. So where do you think this event happened in the room?
The origin?
Yeah, where is the origin? Is it on the left side or the right side?
In the middle.
Right in the middle?
Yeah.
Okay, so so what I want to highlight here is this process of looking at these events and then deciding where it happened. This is one of the types of analysis that we do on our data. So this thing that we do as humans where we look at these pulses and we say, okay, it kind of looks like it happened about in the middle or maybe a little bit more towards the right side of the room or the left side of the room. I'm not sure which side you guys are seeing over there. Is something that we do with our pulses, and that's one of the machine learning applications that we have within our collaboration, is taking all the information out of these pulses and figuring out where did this happen in our data.
Chain.
No, yeah, we have one more. I'm sorry. Okay, we're gonna do this one. All right, one more. All right, we're gonna and everyone has to sing. It can't just be Michaela. Okay, so we're gonna sing. Okay, so does everyone know what their part is?
So, but the people on the left have to be very short and we have to be very high.
Yes.
Okay.
Exactly.
Okay.
And we say,
Okay.
Yeah, okay, I think we've got, all right, so I'm gonna sing this one that goes up to like a real spike. Okay, so 3, 2, 1. Ah! Okay, all right, now you guys can release your chain. You're no longer, so you don't have to pretend to be sensors anymore. Thank you very much. Okay, so here, this is an interesting event. This particular pulse, this has a feature. It's really spiky. And this is actually something that we see in our data. So when we have an event that happens really close to the surface, we have something really spiky occur. And so this is one of the things. So before, what I said was that figuring out where these events happen is one application of machine learning in our collaboration. It took us actually a really long time to figure out that this spikiness was something that was happening and that it was something that we could use to identify where events were occurring in our detector. This is incredibly important. It sounds simple, like, okay, we kind of want to know where events are in our detector, but it's actually incredibly important for dark matter experiments because when you have events on your detector, there's radiation everywhere, and there's radioactive contamination everywhere. And the events that are near the surface of your detector are very likely to be radioactive contamination. So, you know, like you make the detectors and then you put some lithography on them for the sensors, and then you like transport them. And so all that time they're above ground and they're subject to cosmic radiation, and the surface is getting exposed to radon gas, and the wires that you put down for the sensors themselves are radioactive somewhat. So all of this stuff means that, like, if you see an event and it's really close to the surface, it's probably just radioactive contamination. So what we're interested in doing is identifying events that happen near the surface and throwing those away because those are unlikely to be dark matter. Okay, and so this constructing where we think the event happened in the detector is very important to us, and it's something that we're interested in doing as well as we possibly can. When we use traditional methods, of analysis, like fitting the pulse peak, for example, and then using the information from the pulse peak to identify the location of the detector, we throw away about 50% of our events. And we know that that's not necessary. It's just that our methods aren't very good. So we're losing half of our detector volume. It's like we built a detector that was half as small as it actually was. And so one of the things that we're interested in is using machine learning to do a better job of identifying surface events so that we don't have to throw away as much of our detector. Okay, so the other thing that I want to say is, let's just see what time it is. Okay, the other thing I want to say is that you actually can browse, these pulses, and I want to very quickly show you what a typical pulse looks like that we would consider for dark matter. So this dashboard exists thanks to the GC lab, so a huge shout out to them. So this is data that we took that's calibration data. This is actual data from one of those detectors that I showed you earlier. And what I want to highlight is this kind of looks like the pulses that we were just singing. The pulses that we were just singing were very large. So let me show you what a typical dark matter event looks like. A typical dark matter event looks kind of like this. And so this is an example of a typical event that we're looking at. And the question is there even signal there, or is it just noise? This is a classic question, and this is another application of machine learning in Super CDMS. Figuring out and classifying these really small signals and identifying whether or not they look like they're noise and denoising the signals so that we can accurately estimate where they happen in the detector and how much energy they deposited in our detector. Okay, so let's return and also not sure what happened to make it not full screen anymore, but we'll just go with it. Okay, so what I want to talk about finally is this. So let's watch this video for a second. So what we're going to imagine now is that we think that we're taking some dark matter. And so what we've got here is we've got radioactive background. That's the red. The dark matter signal is the blue. And so this is a case that is hopefully much worse than the case that we're detecting, but I want to use this to sort of highlight the problem that we're facing in the dark matter community. So the thing is that our detector can't actually tell us what's blue and what's red. It doesn't have any ability to tell us, oh, that was dark matter, as opposed to, oh, that was a regular gamma ray from some background krypton that you don't care about. And so the challenge that we face is that when we have all of this background, it's really hard to see the signal in there. We can do a bunch of things to reduce the background, and we do. One of them is that we move underground so that we don't have surface radiation. And we can also use highly radiopure materials. That reduces the background. And then we can do everything that's in our power, including machine learning algorithms, to throw away things that are on the surface of the detector that we probably don't care about. So we work and work and work to get rid of all of that background and uncover the signal. But it's a very challenging problem, especially because as this next generation of dark matter experiments are built, we are getting very close to something that we call the neutrino floor, which is where our detectors are going to start being sensitive to neutrino interactions, which is a very small, because we make our detectors sensitive to extremely small energy depositions, and neutrinos can cause extremely small energy depositions. And so if we get down low enough, we start seeing neutrinos. Okay, so this is kind of the problem that we have in the community is how do you really distinguish between what's ordinary background and what's truly dark matter? So I just want to mention one idea that I have, and then we'll stop for questions. So one idea that we have here is this idea of combining experiments. So this right here is SNOLAB. So SNOLAB is actually an active nickel mine in Canada. If you ever want to go see a dark matter experiment or a neutrino experiment, you can actually visit there. You have to do a bunch of training, but you can do it. You're allowed as a member of the public. And then you go down this mine shaft. It's 2 kilometers or about 1 mile underground. So you go down this elevator, and your ears pop on the way down. And then you get down to the snow lab, which they've carved meticulously out of the ground, out of the rock in this nickel mine. And so this is where the CDMS experiment, the new CDMS experiment, will be located. So now CDMS, the experiment, has this problem of identifying what's background and what's not background and distinguishing between the two. The thing is that it's not just a CDMS problem. So these are all, these posters are all different experiments that are highly sensitive, that are at the same location. And so one of the things that we can do as a community is we can take experiments that are co-located, and we can look at the data and we can use all of these other experiments that are all sensitive in slightly different ways to background and signal. And we can analyze all of that data together to get a much better constraint on our overall background, so that we can understand how much of that red background we have, so that we can better extract the blue signal. And so this is an idea, and I want to say this is an idea that really requires a lot of partnership. And so I want to say thank you to the National Science Data Foundation, or the National Science Data Fabric, because they've been talking with me about this. One of the problems that we face when we try to combine data from these experiments is that everyone has their own custom data, their custom analysis software. And it's incredibly difficult right now to combine data across experiments. So this is one of the things that I'm really interested in, is making a platform that allows us to actually analyze data across different experiments so that we can better constrain this background that we're all facing down and that we all have to figure out. Okay, so there's many more slides here, but don't be alarmed. The next slide is the thank you slide. And so all of these slides here are just to have nice pictures depending on what questions you ask me. So let me say thank you so much for your attention. Thank you for singing with me. I really appreciate it. And questions?
Thank you, Emily. So thank you for the presentation. Now we open the floor for question, comment, feedback, curiosity. We have many participants, so I'm sure we have also many questions. Who want to start? Yes, hi.
What kind of machine learning techniques do you use to separate the signal from noise?
Yeah, okay. So I would say that there are a lot. So let me just give you a couple examples. So one of the, let's take a look at some of these, at the signal over here. All right. Okay, so one example is denoising algorithms. So this is something that we're just starting to look at, but we have all of these sensors. Like, so here, right, we have many different lines, not just one single line. And so what we expect is that noise would be correlated on these sensors to some extent. So we're expecting both correlated and uncorrelated noise, and then we're expecting correlated signal. And so these sort of provide some essentially constraints across the signals. And we expect to be able to use denoising algorithms on these. Okay, so I apologize, that's not very specific. That's work that we're just getting started with. So that's one application. Other applications are identifying what we think is noise using, I think that they're called RNNs. I don't know if we have any machine learning experts on here that can correct me, but basically what we do is we take a ground truth and we train on what we think, so what we do is we make simulated data, and then we train a network to distinguish between the simulated data with noise and simulated data with signal injected. And then once we train that network, we can apply that network to our data. And so that kind of gives us a way to really truly establish a noise threshold. And that turns out to be allow us to set the threshold quite a bit lower than we set the threshold with traditional methods. So that's another way that we sort of identify background, because when we say background, one of the sources of background really is, it's just noise. It's not even physics signal. So then the other thing that I'm going to mention is that distinguishing position is a really good way to distinguish background. So we really, it's really true that events on the outer part of the detector are much more likely to be background. And so if we can train a network on features of the pulses, then we can much more effectively get rid of those. So let me just show you a pulse here. So this one actually is really clear. What you can see is there's a little spike. There's a little spike on one of these. Let me see if I can, there it is. You can see it, there's this, so see that little tiny spike right there? So that means that this happened near a sensor. And so this is something that machine learning algorithms are very good at detecting as features. Now, where this gets harder and why this becomes an interesting machine learning problem is because we're generally interested as dark matter physicists in very small signals. And so we need to be able to notice these kinds of features when the signal is close to the noise. And so this is sort of another way that we can use machine learning to reduce that background. Okay, I'm not sure how if that's answering your question, but.
Yeah, it did. Thank you.
Thank you. I have a question about the data itself. So you speak about experimental data that are very complexly collected. I mean, you show the infrastructure. Is it the only infrastructure that collects such data, or there are multiple across the world?
Yeah, so I would say that most of the experiments that are deep underground are collecting this kind of data, where you have some kind of voltage along the y-axis that represents something about the detector: temperature, how much light there is, heat. Okay, that's the same as temperature, sorry. Charge, for example. So we all sort of have some quantity that we're sensitive to, and then we track how that evolves over time. Is that what you're asking?
Yeah, but then you collect this experimental data that are quite hard to reach. And so you have to transfer the data from the experimental facility to the scientists. So what is the process, and how easy is it for scientists to share this data? Are we running out of experimental data and we are forced to use simulations?
Yeah, okay. So I would say, there's a couple different aspects of this. So I would say that it's the physical process of actually transferring the data is relatively difficult, just because we tend to have network problems. So we take the data, we call it below ground, and then we have to transfer the data out of the mine. And so there's this like thin little cable, and all of the experiments are trying to use it. So you have this thin little pipeline, and then you add network trouble on top of that, and you have a little bit of a disaster on your hands. So that's actually one of the things that I'm in charge of. And so people get very mad at me at 2 in the morning, and I have to go and try to troubleshoot a network remotely, which is super fun. So the process is, but we do eventually, I would say that eventually all of us are able to get our data out. And then this mine is in a really remote location in Canada, so it doesn't have high network connectivity. So then we have to very slowly transfer our data off to other like what we call them tier 1 sites. So sites that do have better network connectivity. And then from there, all of the scientists can access it. So the physical process is a little bit grueling. And in general, we kind of all have to be careful that we don't take data faster than we can transfer it out of the mine. And that's actually an edge that we bump up against relatively frequently. We would all like to do, so this is what we call event-based data acquisition. So we wait until something happens, and then we record the data when we think something has happened. One of the things that actually a lot of us would love to be able to do is just record the data continuously, so that we can see everything that happened. But the reason that we don't do that is because we literally couldn't handle the volume of data that would entail. So that's one part. The other part is, once you have the data, how do you access it? And then that still is very difficult. So there's a number of things that sort of make it difficult. One of them is that the sites that we put the data at, we need to put the data somewhere that's supported long-term, that has good backup systems. We can't spend all of this money taking this data and then not back it up very carefully. And so these sites tend to be national labs. And I don't know if any of you, I'm sorry for those of you who work at Oak Ridge, I don't know what your experience at computing at a national lab is like, But in general, it's like if to get an account, it's a little bit tough. And then to log in, it's a little bit tough. And so, so the data is usually sort of kept behind this firewall. It's not necessary. Like this data isn't sensitive information. It's not, I mean, we don't, often experiments want to keep it private, at least initially. But the only reason that it's difficult to get to is because the sites that are secure in terms of backups are national labs, and the national labs are difficult to get into. And then the other thing that makes it difficult to get access to the data is that all of this data is taken by custom data acquisition systems, because we had to make our own custom hardware that is incredibly low noise to read out these incredibly small signals. And so we have a custom hardware stack and then a custom software stack that like like some postdoc somewhere wrote, and so we take the data in totally custom formats. And so it's just sort of an issue of, in principle, it's not difficult to access the data, but in practice, you need to have access to you need to have access to the special national lab, you need to have access to the full software stack. The software stack is not well engineered, it is not easy to install, and so there's just sort of all these problems in getting to the data. And then you also have the problem of experiments being willing to share their data with each other, which is sort of the more human part of it. So there's a number of technical challenges that we encounter along the way. Is that answer your question, Michaela?
Absolutely, and you also give us a good idea of what are the challenges that scientists in your domain are facing, and how computer scientists who work in data engineering could join this effort and help. I think there are a couple of questions from remote. Michael, you want to introduce them?
So we have a couple questions. The first one is from Zaki. And the question is, would it be worth it to place these sensors on the far side of the moon and send back these signals via a relay satellite to avoid the interference on Earth? I'm afraid that denoising might strip the data from important information.
Yeah, okay. So this is actually very interesting. There are actually experiments for dark matter in space, but they generally operate very differently. So these particular sensors, it wouldn't make sense to place them on the moon. And the main reason that it wouldn't make sense to place them on the moon is because there's a lot of radiation on the surface of the moon. Outer space is an extremely radiation unfriendly environment. Right, so that's really the main reason. So if you put these even on the surface, they just light up like a Christmas tree. And so if you put them, and that's on the surface of the Earth. And the Earth has this protective atmosphere around it. So we actually have relatively small amounts of radiation on the surface of the Earth compared to the surface of the moon. If you put these on the moon, they would stop operating, they would just warm up and stop operating. They would have so much signal going through them. So that's really the limitation there. However, the idea of dark matter experiments in space is a really good one. And so there are a number of experiments that are looking for dark matter in different ways that are launched in space. And so the typical way that the satellite dark matter experiments are looking for dark matter is they're looking for dark matter annihilating on dark matter and producing a little bit of extra light. And so there are these satellite experiments that go around and they're looking for an excess in light signal at particular energies.
Awesome. And then we
So
have
join a satellite experiment. That's my suggestion. If you're interested in dark matter in space, the satellite experiments are the way to go.
awesome. Thank you. And then another question from Kai Wen. It said, is comic ray another noise source, or it will be uncorrelated signal across all the detectors so you can filter it out?
Yeah, this is an excellent question. Cosmic rays. Okay. Cosmic rays are in case anyone's not familiar with cosmic rays, this is the day of finding out that particles are streaming through you constantly and you didn't know about it. So cosmic rays are another type of radiation that was constantly streaming through us, about 1 per foot per second. So every second you have a cosmic ray ripping through you and ionizing a bunch of tissue in your body. And so that's fun. And in general, the higher up in our atmosphere protects us against it. So the higher up in our atmosphere you go, the more cosmic ray radiation you are exposed to. So when you fly, you get a lot of cosmic ray radiation. And when you go deep underground, you get much less cosmic radiation. So cosmic rays are absolutely a source of signal in our detector. Usually, we can easily spot them because they create a very large signal. However, the danger of cosmic rays is that a cosmic ray comes through and it doesn't go through your detector, it goes through the rock that's right next to your detector. And as it's going through the rock right next to your detector, it interacts strongly with the nucleus. And that nucleus explodes because these cosmic rays are traveling nearly the speed of light. And that nucleus explodes and neutrons go flying everywhere. Neutrons are neutral particles and they can wiggle in to our detector. And so then what we have is we have a cosmic ray that's gone through, and then we see a neutron event, which looks a lot like a dark matter event. And that is, in fact, one of our main sources of background deep underground. And that's one of the reasons that partnering with a bunch of other experiments may be a very wise idea, because all of those experiments can also see cosmic rays and neutrons. And so if we see a neutron in our detector or a signal that looks like a dark matter candidate in our detector, at the exact same time that another experiment sees something that looks like it could be a dark matter candidate, it's not a dark matter candidate. It's neutrons from a cosmic ray that happened nearby and exploded a nucleus. So yes, cosmic rays, they're tricky. They're tricky. They're fine if they go straight through your detector, but if they go near your detector and explode a nucleus, they can be a very serious background.
Awesome.
Other questions? Yes. Yeah.
Hi, Amy. Fantastic talk, first of all. So you mentioned that a challenge with newer sensors was that they were maybe more biased towards detecting neutrinos, I think you mentioned, rather than dark matter signals. So I'm not really knowledgeable enough with that dark matter, and it's actually the first time that I've heard about neutrinos. But I'm curious to know what's actually the challenge with that. Like, does it actually exacerbate the problem of background noise? Like, are these neutrino signals harder to denoise than the other ones? Just want to hear your thoughts.
Yeah, absolutely. This is a great question. Thank you guys for these wonderful questions. Okay, let me go back to a picture here. Okay, let's go back to this picture. So this picture right here, what this is showing is that we have something that's coming in and it's hitting the nucleus. And so what we're sensitive to is we're sensitive to stuff that hits a nucleus or an electron, and then that creates some vibration in the crystal. So the thing is that there's a lot of stuff that can hit the nucleus. Neutrons can hit the nucleus. They're very good at that, or they're relatively good at that. They're great at it compared to dark matter. Neutrinos, it turns out, can also hit a nucleus and make it move. And then we hope that maybe dark matter would be able to hit a nucleus and make it move. So the problem that we have is that all of these signals, like if something comes in and hits a nucleus, that it all looks the same to us. We don't have any, we have the ability to say something came in, it hit a nucleus, it deposited this much energy, and it happened about in this location in the detector. That's all we're able to say. And then the question is, what is it that hit the nucleus? Was it dark matter? Was it neutrons? Was it a neutrino? And so what we have to do is we have to be able to understand our background extremely well. So I guess what I would say is we don't have any way to distinguish those possibilities. The only thing that we can do at that point is go to a physical location where those things are where we're unlikely to have neutrons. And we can't really go to a location that is unlikely to have neutrinos or dark matter. So we can try to get rid of the neutron background by digging ourselves deep in the ground and then making sure that all of our materials are very radio pure, and then watching out for cosmic rays that could be creating neutrons. So we have sort of the ability to get rid of neutrons, or most of our neutrons, but we really don't have the ability to distinguish between neutrons, especially low energy neutrons, dark matter, and neutrinos. Anything that hits our nucleus, it just looks the same in our detector. And so what we have to do at that point is we have to have a very strong understanding of our background, so that when we go to this plot, we can say, okay, I know exactly how many counts of this we expect to be neutrons. So let's take out that number of counts. And then we can say, okay, and I know that based on my other experiments around me, I know exactly how many counts I expect to be neutrinos. So let's take out those counts. And then you're either left with something, a number of counts that's consistent with 0 or inconsistent with 0. But I think what I'm hoping you can see with this is that if we don't accurately know how many neutrons to take out and how many neutrinos to take out, we have no way of saying how much dark matter we saw or didn't see.
So thank you. I have a question that is a little bit more provocative. And at the same time, also is a curiosity. So a couple of years ago, we had this fantastic news that we have been able to capture gravitational waves. And then recently we saw a picture of the black hole and it captured our imagination. Now, let's say that in a couple of years, you, Amy, with your team of researchers identified clearly dark matters. Why does it matter for us?
Yeah. Okay. This is a really good question. So I would say it really matters for us because it really shapes everything about our universe. So it shapes everything from how the first galaxies evolved to how the first stars evolved and how the universe sort of continues to evolve. So we sort of have these, so if we're thinking really long time scales, it affects whether or not the universe is going to keep expanding or whether it's going to shrink back down on itself. So dark matter is something that is pulling the universe together because it's matter. And so it has that gravitational attraction that pulls everything in. And then we have dark energy that's pushing our universe out. And so depending on what the ratio is between those two, it sort of determines whether or not space will keep expanding or whether we'll all shrink back down to a marble. So on the really long time scale, it sort of determines the stability of our universe. So I think that that's a really compelling reason. The other thing that I would say is that if we're able to detect dark matter, it means that we have detectors that are sensitive to some of the smallest signals that are recorded ever in human history. And this actually has a huge amount of practical implications. So for example, nuclear monitoring. If we want to monitor nuclear reactors and make sure that they're being used for energy production rather than weapons production. This is something that could be a very small detector that's capable of doing that. We can understand processes in the sun because we can look at the neutrinos that are coming from the sun, the high energy neutrinos at least that are coming from the sun. So the amount of application that this has, if we're able to successfully detect these incredibly small signals, is really broad. Let me just say one more application that I think is particularly interesting. So one of the applications of understanding a small pulse like this well enough to be able to definitively say that we've detected something that is not background is we have to understand how energy is deposited in materials, right? So like when we were sensors, we felt the heat and then we sing, right? So that was sort of our procedure. These lattice vibrations are actually not very well understood at very low energies. And the reason that that's interesting is because when people are trying to make fusion reactors, for example, one of the issues that you run into is material damage, extensive material damage. And the material damage is caused by neutrons that are interacting in that material, just like we expect dark matter to interact in our detectors. So these detectors are actually a window into the material damage process. And so if we're able to say that we understand these signals so well, what that will mean is that we actually have really unique data to understand material damage processes as well. So I think there's sort of universal implications of what this dark matter means. And I think there's also the really practical implications of being able to detect signals that are that small and understanding what's happening in our detector to such a precise level that we're able to detect dark matter. And so I think all of those are going to have really large implications on like technology, hopefully energy generation, and also sort of cosmological models of the universe.
Thank you. I would like to finish with one last question that probably is very short to answer, but important for us in this interdisciplinary domain. If you have a wish of 3 wishes that you want computer scientists deliver to you for your research, what are your 3 wishes?
Oh my gosh. Okay. All right. I'm going to make each one really big. So I think my number 1 wish is for computer scientists to help us solve our data problems, solve our data access problems. So I think this is an incredible wealth of data. Each experiment has an incredible wealth of data, and it's much stronger if we're able to combine it together. And we're only going to be able to do that if we can access the data easily. And then other things like the other thing that this would really help with is cross collaborations. So this thing that I mentioned about materials damage data is incredibly difficult to get. And this is the detectors that we operate have an incredibly unique window on it. And one of the things that makes this collaboration not happen is because it's so difficult to share data outside of our collaboration. So we could talk to material scientists, but it would take them years to be able to understand our data, access our data, and work with our data in the way that they need to. And so I think that just an amazing amount of science would be possible if we could easily share our data, even within our own collaborations, but especially across collaborations. So that's my wish. That's my wish number one. Wish number two, I don't know how realistic any of these are, but they're my wishes. So wish number two is reproducibility. So there's and some way to capture all of the metadata. So one of the things that I didn't talk about is all of the different physical aspects that go into operating these detectors. It's enormous. We have to keep them cold. We have to keep radon gas away from the center of the detector. We have to be deep underground. The pressure of the air affects how much radon gets into our experiment. It's just wild. It's wild how much metadata there is that we really need to capture to really truly understand our data. We need to know what the humans were doing. We need to know if the HVAC system was turned on. That introduces noise. It's not dark matter. It's just the HVAC system turning on. So just everything about our facility, about the hardware. And so capturing all of that material, or like capturing all of that information, and then capturing all of the different aspects of our workflows that we use to analyze the data is just incredibly difficult. And I don't think it's an unsolvable problem. I suspect it's one that computer science probably has some really good answers to. It's just difficult, and we haven't done it, and we haven't done it within the physics community. We don't have that kind of expertise really. So that's my second wish is, you know, how can we truly capture all of our metadata, and how can we make our workflows reproducible? That kind of sounds like two, but I'm going to say it's just one. And then I think that my third wish is to have computer scientists collaborate with us on machine learning applications, because we have I think that what we've seen in the last 5 years is that machine learning applications are actually improve our existing algorithms. But we really don't have a lot of knowledge of this in our community. And so mostly what we have are physicists who have sort of self-studied on machine learning. And that's very different than someone who really has deep knowledge and did their, PhD work and does their research on machine learning. And so the ability to collaborate extensively on how do we approach some of these problems, like how do we denoise? How do we distinguish between noise and signal? How can we best reconstruct the energy that was deposited in our detector? These are all questions that physicists can tackle, but we're not going to tackle them as well if we do it without computer scientists.
Well, thank you so much, Amy, for this fantastic talk.
Thank you guys so much for being my audience and participating.
And for challenging us. We have a mission now as computer scientists we have 3 wishes to realize it. We hope we are able to get closer. Thank you so much to you. Thank you to the participants here in the room and remotely. We will have soon an announcement of a new seminar. We are not ready yet to reveal the speaker, but stay tuned. And Amy, have a great rest of the day, and success with your research. Bye, everyone.
Thank you so much. Thanks, everyone.